I hope you had a good evening. So plan for today, bunch of stuff talking about the pedagogical content of the intro course today, and a little bit this afternoon about infrastructure and the technology to run the course, in case you want to try to learn from how we scale it. And then tomorrow morning we'll broaden our scope a bit, so tomorrow morning you'll hear about other courses and the rest of the program, but today focused on this intro course. Tonight we'll have, this evening, just get together for a social occasion, drinks at a local bar, so afterwards follow Anthony and we'll organize at the end of the session. Anything on your mind before we get started? Concerns? Okay. All right, so what I wanted to talk about first was hypothesis testing, because this is the way that I wish I'd been taught hypothesis testing. And after doing a couple of iterations, changing how we teach inference and hypothesis testing, I'm now happier than where we started. So I thought I'd show you. It's one model that you could consider for how to teach hypothesis testing. And the theme here is testing theories about the world. Right? If you think about the classical view of science is that we have some theory about the world that makes some predictions. You know, I don't know, our laws of gravitation predict that if I drop this bowling ball and this other ball from the leaning tower, they'll land at the same time. That's a prediction, right? And then we go gather observations from the field, and we compare the observations to the predictions. And if they disagree, then we've got evidence that should make me doubt my theory, right? Classic view. What's new here is that we've got randomness in town. So you drop the two balls, and you don't get the same answer every time. Instead, maybe our experiment is something that involves some random sampling from a population, maybe. And my theory makes a prediction about the results I'm going to get in that random sample, but it won't be the same every time because there's some randomness in the random sample that I draw. There'll be some variation in the results. And so now the predictions say something a little bit fuzzier, that, you know, maybe it'll follow this distribution, or it'll be most of the time in this range. Okay, so this is the theme for how we structure the hypothesis testing. And the ordering here, after we've tried a bunch of different orderings, here's the latest ordering that we're the most happiest with so far, is that first we teach modeling. Like, what's a model about the real world? How do you simulate, given a model, to simulate the world, and use that as a way to get predictions from our models of the world. So our models make predictions about what's going to happen. Then we talk about how to compare the predictions to the observations. And we want to find out whether the observation is consistent with the prediction, and so we need some way to determine what counts as consistent. So we need some way to measure the extent to which something's consistent, and that leads us to classical things like p-values and so on. Okay, so that's kind of like a very high-level picture, and the ordering is you start with models and making predictions from them before you start to say anything about hypotheses or hypothesis testing or anything like that.
When you say that's the best ordering, what other orderings?
I don't know if it's the best ordering. It's the the one that I'm happiest with so far. The other orderings is we used to start from, here's the idea of hypothesis testing. And then let me develop how to do it. So we started from the end goal, and then on the way, all the stuff came in, models and predictions and simulation, and all happened all at once. Another difference here is maybe starting from a single model rather than starting from two hypotheses. But that's kind of a small minor thing. So this is the overview, and I thought what I would do is I'd maybe show you some more details of like slides and how we talk through it with students. And you can maybe see how this is similar or different to other ways of teaching it and form some opinions about what you like or what you don't like, and we can discuss as we go. Yeah?
So I know this is too advanced for this course, but to what extent did you think about Bayesian versus frequentist paradigms for teaching? Because I know, like p-values are increasingly controversial, and
Yep.
frequentist thinking is not particularly intuitive, and Bayesian thinking is a little bit more intuitive, at least for beginners. So
Yep.
is that something
Yep.
that you thought about incorporating or decided?
Definitely thought about, and that was on that list that was, like 2 years or 2 semesters worth of material. And what happened was when we talked to folks from different disciplines who were going to use this, we heard overwhelmingly, students have to know what hypothesis testing and p-values are. And there weren't that many advocates for Bayesian reasoning. And so this had to be in there, and then there just wasn't space to, yeah.
What's the prerequisite for this class? And do your students supposed to know the basic concept of mean deviation before they do this, or what's the context?
Yeah, no prereqs. So, high school, like algebra. Definitely don't assume they know standard deviation. They don't even see standard deviation at this point in the course until, I don't know, halfway or 2/3 of the way through. And mean, I think we probably assume they know what it is, but we maybe just mentioned for 30 seconds again what a mean is. But we don't assume anything more than that. Like we don't assume they know what a median is or what percentiles are. Or does that make sense?
Any discussion about linearity, non-linearity, when you talk about models?
Not here. When we talk about correlation, associations, linear regression, we do. So we introduce this notion of association, which might be any pattern. And then when we talk about linear regression, we talk about linear correlation and nonlinear associations. And so that's where it comes in. Our models here are mostly more emphasis on like the probabilistic model, like the randomness underneath it. And we're typically trying to frame them somehow as sampling, because we've introduced the notion of sampling. By this point, we've talked a little, just very briefly about probability, and so those are the 2 concepts we can build on. Yeah.
How much math notation do you have in the course, in the sense that do they know the difference? So when you talk about mean versus X bar, what they mean?
No, there's no bars, there's no, none of that. You can take a look at the slides. I'll show you some. I picked out some of the slides we use. We're trying to avoid that. There are a few exceptions. You'll see, like when we're teaching linear regression, a little bit of notation starts to enter. There's some formulas in there, but trying to avoid it. But we do talk about the concepts. So remember that in about 2 slides, like the notion of the population parameter versus the estimate. We're trying to be very clear about the distinction between that. So maybe getting at the same idea, but not through notation, but through terminology and talking explicitly about it. If that's what you're thinking.
Yeah. I was just wondering if adding that in without necessarily focusing on it is beneficial in some way.
Be a great experiment, see what happens. Okay, so here's where we start. So I thought what I'd do is I picked out some slides. And I'm not going to I'm not going to lecture at you like I would the students, but I'll highlight a few things that we mentioned as we go through this. So we start by talking about probability distributions. And this is one way to explain it is kind of like thinking about a histogram. And we introduced the notion of an empirical distribution. So we have the true probability distribution that would be obtained if you sampled from some population. Then if you draw some samples, you can form an empirical distribution. And then we talk about introduce the idea of statistical inference. Okay, so the broad goal here is we've got some observations that were obtained through some sampling procedure from some random samples, and we want to use that to draw some conclusions about the population they were sampled from. Okay. Right, so we're trying to estimate something about the population. And this is where the point you raised about in the population, there's some fixed unknown value that we're trying to estimate. And we can get from our sample an estimate of that. The estimate depends on the sample. So if you drew another sample, you'd get a different estimate each time, even though the true value is not changing. So we introduced some terminology, and this is where we're kind of drawing this distinction between the parameter is the thing associated with the population, the true value that we don't know, that we wish we could, but we can't see because we don't have a God's eye view, and the statistic, which is this number that's calculated from the sample, our estimate, effectively, or something to help us estimate the parameter. And we talk a little bit about how to measure, how good an estimate is. How would you tell, if I've got an estimation procedure, how would I tell whether that's a good one or not? And you can do some simulation, and you can look at the distribution of the estimate. And if you simulate, in a simulated world where we start out by assuming I know all the data and I know the full population, then I know what the parameter is, and I compare the known parameter to some estimates I got by simulating this procedure. And if I simulate it many times, I can look at the distribution of the estimate and compare the two, and that tells me something about how good my estimator is. So we can talk about bias and variance in the estimator. And we can introduce the notion of the probability distribution of the statistic. Here's what the distribution of the statistic is. It depends on the random sample. It's some distribution. You may or may not be able to calculate it. If you wanted to try to figure it out by looking at all possible samples, there's way too many samples to enumerate all of them, so it's often infeasible to get this exact probability distribution. So what we instead do is estimate it by looking at the empirical distribution. So this is the simulation part. And that's kind of the background. And then here's where we start to get into something that's a little closer to the hypothesis testing. So we talk about given some data, trying to draw conclusions, figure out what conclusions we can draw, and sometimes want to choose between two possible theories about the world. Really, it's kind of one theory about the world, like that chocolate has no effect on whether you're going to get a heart attack. And then there's a second one, which is, whoops, that theory is wrong. Okay. So at this point, before trying to develop things too formally or systematically, we do an example. Start with an example. And here's an example that I love because it's so engaging. So let me tell you about this example. It's a Supreme Court case, Swain v. Alabama from 1965. And what happened in this case was this, this man, Robert Swain, a black man, was convicted of a horrible crime in Talladega County in Alabama. He appealed, and the appeal went all the way up to the Supreme Court, and it was multiple grounds, but one ground of the appeal was I'm entitled to a jury of my peers, and the jury was not representative. And what happened in this case, there were a whole bunch of fairly egregious facts. It came from a county where at the time 26% of the population was black, and yet the final jury was zero blacks on the jury. There was a bunch of evidence supported by the defense attorney to suggest potentially bias at multiple stages of the process. But the one we're going to focus on in this example is, let's just look at that bottom line number. I mean, that's a rather remarkable gap there. You start with a population 26% black, and you end up with a jury of, I think it was 11 people, of which none were. All right? So one of the arguments in the appeal was there's no way this process was fair. Look at how extreme that is, right? And it's not just that the final jury was all white, but if you look at the jury panel, then that was also, distribution looked fairly different from the county. So I don't know if you know what a jury panel is, but the way the jury process works is you start with the eligible people in the county, and the county draws up a list of eligible jurors and then selects supposedly randomly from them to construct a panel. Those are the people who have to show up for jury duty and like sit in that courtroom, and some of them get questioned, and from those are selected the final jury. All right. So the process, both the, for sure that first stage of the process, selecting the jury panel from the population, is supposed to be random and representative of the population. All right. So the Supreme Court ruling was, you can read the ruling. So the Supreme Court denied the appeal and said, basically, I can see the difference, but doesn't seem to provide evidence of systematic discrimination. Okay, so jump into this and you say, well, okay, now we have some statistical knowledge. This is an empirical question that we can answer. Is it plausible that if the process really was random, and you start with a population that was 26% black, that you would end up with only 8 out of 100 on the jury panel being black? How can we figure that out? Okay.
Got a
Yeah.
question. I'm just wondering, is it going to be sensitive if we include the quoted term in there in class, or I don't know, in your past class? I just find that it might, I mean, like, you have a general statement that just says maybe, that it was felt that blacks were, well represented. I think that's one thing. But when you actually call it out, I'm just wondering if some students might take offense to that.
There's definitely a potential. I haven't had that happen yet.
I'm just thinking like rekindling old stuff,
Right, for sure.
I'd rather not have that happen.
Yeah. There's a lot more experience in this room than I have, so if others have thoughts on that, feel free to jump in.
So I would say, sitting here listening to it, I'm not offended as a black person. What I do wonder is if there's examples of the reverse, where someone who is white was acquitted because they were white, in order to provide the other side of the coin. I think that would be a way in order to minimize anyone feeling offended. So bringing up a more recent case, of black men being murdered by police and how cops get acquitted. That might be a way in order to provide a different conversation. I don't particularly like the word Negro, but that's just my personal thing. But this is 1965, so I think continue to talk about the time is important. At least letting students know that this time, this was the terminology for black people.
Yeah, my name's Carly. I'm from the University of Illinois, and I teach a class called Stat 100. It's huge. There's over 1,700 people that take it each semester, and we actually have this exact example in our notebook. And I specifically don't do it because of that fact that I have had students, especially with such a large class. There's always going to be people that are offended by something, and so I generally skip this example, even though I think it is a really powerful example, and it proves a good point. But I guess we found other examples that aren't as controversial to use. So that's just what we do. But we use the Friedman approach, so I've seen this example before.
I will say that I've gotten very good response from the students to this. Like the
Share some other
yeah.
presentations instead on the Slack channel?
Yeah.
Definitely. Yeah, I can do that.
Okay, so then we look at how we would assess this. At the time, Supreme Court justices obviously didn't have the benefit of what we're going to learn in this class, so we can figure out how we would assess this using some of the tools we've developed. And what we can see here is we need to identify what's our theory or a model about the world. So our theory or our model says it was fair. It was truly random. There was no discrimination in the process of selecting the jury panel. And then that will make some predictions. And we're going to want to compare those predictions to the actual facts on the ground. And how we're going to do that, we're going to need to select a test statistic to summarize the sample. In this case, the sample is the jury panel. And we need to choose one that's going to help us evaluate the theory. Okay. So then at this point we start to take the data and we go to a notebook and we start to walk through doing some simulations with this model, working out how to develop the code for that, and then looking at empirical distribution of the test statistic and all of the classical hypothesis testing stuff.